Okay. Good afternoon, everyone. Now we are going to start the step. The last time we had started the gas laws. Under the gas laws, we discussed about the properties of the gases, and then uh, we discussed about the ideal gases. And we learned that the ideal gases are gases which have no intermolecular forces between each other and has point masses. That means they do not occupy a volume. Okay. So those are ideal gases. Then for the ideal gases, we learned the ideal gas equation that was PV equals nRT. The ideal gas equation is PV equals nRT. Then we learned about the Boyle's. We learned the Boyle's law. After learning the ideal gas equation, we learned the Boyle's law, that is PV is a constant. From this we derived P1 V1 equals P2 V2, and we made some sums. And we learned its graphical representation as well. We learned how to represent the Boyle's law graphically as well. We learned that once the pressure increases, volume decreases, and once the volume increases, pressure decreases likewise. Okay. Right. So those are things that we discussed under Boyle law. So today we have to start the Charles law, third one. Okay. Third law that we have to start today is the Charles law. Right. The third law, that is Charles law. Right. So let's learn what Charles law means. Now, the Boyle law means that it is the uh, pressure volume relationship at a constant temperature. The other temperature is constant. In Charles law, it is the volume temperature relationship at a constant pressure. Okay. That means for a given mass of any gas at constant pressure, the volume is directly proportional to its absolute temperature. That was proposed by Charles. Right. So we can write the law. You can write down at a given pressure. Sorry, we can say the volume of a given mass of any gas the volume of a given mass of any gas at a given pressure or at a constant pressure the volume of the given mass of any gas at a constant pressure is directly proportional to the absolute temperature of the gas. It's directly proportional to the absolute temperature of the gas. This is called the Charles law. It is called the Charles law. Accordingly, also we can say that the volume is proportional to absolute temperature. We can write it. The volume is proportional to absolute temperature. Then we can put a constant. So V equals to K. Then we can substitute V over D. That is a constant. Okay. V over T is a constant. This is constant. Right. Then we can note down in a separate point. For a general case, when the change occurs from for a general case when the change occurs from V1 T1 to V1 T1 to V2 T2 V2 T2 at constant pressure V1 over T1 equals to V2 over T2. V1 over T1 equals to V2 over T2. Right. So that's the relationship. So we can represent this relationship graphically. Can note down in a separate point. For the ideal gases, for the ideal gases, for the ideal gases, the study of the effect of temperature the study of the effect of temperature on the volume of a gas on the volume of the gas on the volume of the gas if the pressure of the system is kept constant if the pressure of the system is kept constant for a fixed amount of a gas for a fixed amount of the gas. The ideal gas equation can be rearranged. The ideal gas equation can be rearranged as follows. like this. V equals nR over P into T. Right now, they are N is the numbers of moles. So we are considering a fixed amount of a gas. R is the universal gas constant, and P is the pressure that is also constant. Here we are considering a constant pressure. Therefore, the whole part of this equation is a constant. So therefore, volume equals to constant times T. V equals K. Then you cannot have the changes in the volume of a gas. The changes in the volume of a gas with respect to temperature. With respect to temperature change at different constant pressures, can be shown as follows. Can be shown as follows. Okay. Now we know that V equals K. Now this is Y equals mx by T. You know? Y equals mx by. So y-axis is the volume, x-axis is the temperature. So now we are taking the temperature in Kelvin scale. If it is so, it changes like this. See, at the pressure V1. At the pressure of T2. Then at the pressure of T3. Right. So it will be changed like that. Right. The pressure changes. Now this is the highest pressure, P1. Then P2 and P3 is the lowest. P3, P2, and P1 likewise. Okay. So that is once we use the Kelvin scale. If we use the Celsius scale, Here you see the center scale, it's like this. So it will start at minus 273.15 because that is the Kelvin zero. See, in the Kelvin scale it is zero. Okay. The shape of the graph will be the same. This is the T1 vector. Then T2 vector. Then T3. Your thing, T1 is the highest and T3 is the lowest. Is it clear now how it changes? Because this is y equals mx side equation. All right. Okay, so you can quickly draw it. Did you finish writing this part? Yes. If you have finished writing this, okay, then we have written a sentence. So below that sentence, we can show these two graphs. I will keep stopping now. Right. Then we can move on. Right. Now this is the Charles law. Right. So let's write the question regarding the Charles law. Right. You can note down this question. The volume of argon gas cylinder. The volume of argon gas cylinder at 27 degrees Celsius. The volume of argon gas cylinder at 27 degrees Celsius and 1 into 10 to the power 5 newtons per square meter pressure. Is 20 cubic deciliters. Is 20 cubic deciliters. If the temperature is changed to 400 Kelvin, if the temperature is changed to 400 Kelvin while keeping the pressure constant, calculate the new volume of the gas. Calculate the new volume of the gas. I'm going to make it for, shall I do it? Okay, you better try it. Now you better understand the things that they are asking. Right. Right. Now it says while keeping the pressure constant. You have to find the new volume, and the only thing that is changed is the temperature. Right, quickly, I'll give you 5 minutes. Yes. Pascal. Yes. 1 Newton per square meter is 1 Pascal. Shall we discuss? Yeah. Because cubic precipitation is not just like right now. Here it says pressure constant. Constant pressure means we can apply Charles law. We can take the assumption applying Charles law. We can say V1 over T1 equals to V2 over T2. V1 over T1 equals to V2 over T2. So volume 1 equals 20 cubic decimeters, that is 20 into 10 to the power minus 3 cubic meters. Temperature there is 27 degrees Celsius, that means 300 Kelvin. New volume, that's the thing that we need to find out. Temperature is 400. And then V2 equals to 20 into 10 to the power minus 3 into 400 divided by 300. So V2 will be 0 gets answered of 80 divided by the power minus 3 cubic meters. So 80 divided by 3 80 divided by 3 is 30, 36. Sorry, 26.6. Why do I? Yeah, I get maybe. Yeah, answer will be 26.6. Now we were discussing Charles law last time. Did you join on that last time? Did you watch the recording? Yeah, I have watched it. Okay. Come on. So there we discussed about ideal gas equation and Boyle's law, and today we start with the third law, that is Charles law. It is the volume temperature relationship at constant volume temperature relationship at constant pressure is called Charles law. There, V is proportional to T, absolute temperature equals to KT. And from there, we can get this relationship V1 over T1 equals to V2 over T2. So there we have done. Okay, did you get the answer? This one? So you will get the final answer. Yeah, we got the 10 from minus 3 cancel out on both sides. Therefore, we get final answer. So if you have found the final answer, then that will be 26.66. Online people, do you understand it? We want to go to we want to go to the next. We want to go to the next. Is it okay? Yeah. Have you done these things? No. I just say okay. So you can comment because the first part of the sheet. Right. Then that is the Charles law. Then the fourth law that we have learned is the combined gas. We call it the combined gas. You can write it, okay? combined gas law. For one combined gas law. Did you write it? So the combined gas law is a thing like this. Now, now we know that almost all the gases they behave ideally. They have an ideal behavior at high temperatures and low pressures. Okay. So that means they behave in different ways with respect to their pressures and temperatures. So while changing the pressures and temperatures, the gases behave in different manner. So if the amount of a substance is measured per mole, then we can express the ideal gas expression as P1 as Pb over T. Okay, because N is the numbers of moles and R is constant. So if we subject NR, then we can write it as Pb over T. If the numbers of moles is the same for the initial and final conditions, then we can equalize P1 V1 over T1 equals to P2 V2 over T2 likewise. So that is called the combined gas. Is it clear? So that is a combined gas law. Okay, now let's learn it. Right, you can note down. Since all the gases behave the same way, since all the gases behave the same way with respect to pressure, volume, and temperature, since all the gases behave the same way with respect to the pressure, volume, and temperature, come on. If the amount is measured per mole, if the amount of measured per mole, then the ideal gas equation can be rearranged so we can rearrange it like this. We have PV equals nRT, ideal gas expression. So if we subject NR, that is PV over T. NR equals PV over T, we can rearrange it like that. So if we consider two different conditions, can say for initial condition, We can say NR equals to V1 over T1. Okay. V1 over T1 by using this equation. Pressure volume 1 divided by temperature 1. Then for the final condition, again we can subject NR, that will be P2 over T2. That's the second case. Simply P1 over T1. Then other one is P2 over T1. Right. Then we can equalize these two equations because NR are the same. So we can equalize 1 into 2. 1 equals to. So therefore, V1 over T1 equals P2 over T2. This is called the combined gas. Okay. T1 over T1 equals P2 over T2 is the combined gas flow. Did you understand? Right. Okay. You can write it. So let's see a question. Hydrogen gas balloon occupies 5 cubic meters at 27 degrees Celsius. And 1 atm pressure at 27 degrees Celsius and 1 atm pressure. When the balloon rises up, when the balloon rises up, it attains a temperature of minus 23 degrees Celsius. Minus 23 degrees Celsius and a pressure of 0.2 atm. Pressure of 0.2 atm. Calculate the D volume of the question. You can try it first. Now find what are the constants and what are the things that are varying. Right. So did you make it? No? What's the answer? Rangan? 2.083 meters. Here 2.083. What's the answer? What's let's simplify it by now. Amna, what's the answer? Did you get an answer?
Yes, sir.
So what is it? What's the answer?
Is it 20.83 simplification issues?
20.83 cubic decimeters. Anything what happened? What happened? Come on, now we have to apply the temperature in Kelvin scale. So තමයි last week ටික බලුවා නැත්නම් ඒකේ ප්‍රශ්නේ. Last week recording බලුවා. Yes. Always we have to substitute the values for these equations in SI units. The SI unit for volume is cubic meters, not cubic centimeters or decimeters. It's cubic meters. So if the values are given in cubic centimeters or decimeters, we have to convert it to cubic meters. Then the temperature, SI unit for the temperature we use is Kelvin. Celsius is also a standard unit, but here for this we use absolute temperatures. Then what's the standard unit of the pressure? SI unit of the pressure? Pascals or newtons per square meter. Both are equal. Right. So for this one, now hydrogen gas balloon occupies 5 cubic meters at 27.1 atm. When the balloon rises up, it attains a temperature of minus 23 and a pressure of 0.2 atm, and it will reach a new volume. So all these three pressure, volume, and temperature are changing with each other. So therefore, P1 V1 over T1 equals to P2 V2 over you have used as ATM. Okay, so pressure, initial pressure was on 1 atm, so it is 1 into 10 to the power 5 pascals. Then the volume was 5 cubic meters. And the temperature was 27 degrees Celsius. That means in Kelvin scale, what's the level? 27 plus 273, that is 300. No? Equals to P2, it is 0.2 atm, that is 0.2 into 10 to the power 5 pascals. Into V2, that's the thing that we need to find out, V2 volume. And the T2 temperature is minus 23. So minus 23 plus 273 means 250 Kelvin, right? Now we need to simplify. We need to find out the V2 value. Okay, so 10 to the power 5 gets cancelled off. We can find out V2, that is 1 into 10 to the power 5 into 5 into 250 divided by 300 into 0.6 into 10 to the power 5. The 10 to the power 5 gets cancelled out. 0 gets cancelled off. Now we have to simplify. 5 times 5, 5 times 6. So it is 25 divided by 1.2. Answer will be 20.83 cubic meters. 20.833 cubic meters. Is it clear? I think I would do right. Defect expert in the division. With the division. I noticed. That means you know chemistry, what you don't know is maths. Right. So I cannot support with your maths skills. Okay, now the my students are asking, should we take the answer till the third decimal point? No, you can end with two decimal points as well. At least you have to take the answer to two decimal points. It's better if you can get to the third decimal point, then the answer is more accurate. But it's okay. Okay. Now, did you understand how to apply the combined gas equation? Okay. That is combined gas. Then the fifth one, the fifth law that we are going to learn here is Avogadro law. You find Avogadro law. Right now, here the Avogadro law means that it is the relationship between the volume and the numbers of moles. Now, Boyle law is the relationship between the pressure and volume. Okay. Boyle law is the relationship between pressure and volume. Charles law is the relationship between volume and temperature. Okay. The combined gas law is the relationship between pressure, volume, and temperature. And Avogadro law is the one which has a relationship between volume and temperature. It's a volume and numbers of moles amongst of the substance. Okay. So let's write the definition of the Avogadro law. You can say equal volumes of all gases, equal volumes of all gases under same conditions of temperature and pressure equal volumes of all gases under the same conditions of temperature and pressure contain equal number of moles. So let's see the relationship between these two. Here we can say the volume is proportional to the numbers of moles. Volume is proportional to the numbers of moles. That is the equation. simply. Okay. So we can put a constant here and we can write this as V equals Ka. Right. Now a constant here, that means in 1 mole of a gas, there are that is in 1 mole of a gas or any substance, there are Avogadro number of molecules. Okay. There are Avogadro number of molecules in 1 mole of a gas. So that value has been determined as 6.022 into 10 to the power 23 per mole. Right. So we can say in 1 mole of a gas, now I have finished writing up to this point. Okay, then you can say in 1 mole of a gas, in 1 mole of a gas, it has been determined that the number of molecules is to be in AOL, that is equals to 6.022 into 10 to the power 23. 6.022 into 10 to the power 23. It's better if you can remember this value. Because I can remember. Right. But usually this value is given in the question paper. But you have to remember that this is the Avogadro constant. Okay, NaOL, that is called the Avogadro constant. Now this is the Avogadro constant. That's Avogadro constant, and for any given gas, in 1 mole of the gas, it has this much of molecules. So it's a very large value, no? 10 to the power 23 means 6.022 into 23 zeros, no? Right. Did you write it? Avogadro's constant? Yeah. Then after writing that, you can say the Avogadro law can be easily understood. The Avogadro law can be easily understood with the help of ideal gas equation. Okay, PV equals nRT. The ideal gas equation is PV equals nRT, and we know that the Avogadro law says the volume is proportional to numbers of moles. So let's subtract volume here. So volume equals to n times RT over P. N is the numbers of moles. So numbers of moles into RT over P. All right. Now we learned that 1 mole has Avogadro number. Okay. Here we have 1 mole. So the number of molecules there will be Avogadro number. Is it clear? In 1 mole of a substance, in 1 mole of a gas, we have Avogadro number of gas molecules. So therefore, we can write it like this. Avogadro number equals to Avogadro number equals to number of molecules divided by numbers of moles. Or else you can say number of moles equals to number of molecules divided by the Avogadro constant. We know that there are Avogadro number of molecules per one mole. Then we have numbers of molecules. If we divide numbers of molecules by Avogadro constant, that will be the numbers of moles. Is it clear? So we can simply say, now we know that in one mole of a gas, we have Avogadro number of molecules. So to find the unknown numbers of molecules, we can multiply the Avogadro's constant by the numbers of moles. Did you understand? That means in one mole we have Avogadro number. So to find out the total number of molecules, n equals Na times n. So we can rearrange this one and subject simple in numbers of moles, that is n divided by n. So we can replace these numbers of moles by that n over n. So V equals number of molecules divided by Avogadro constant times RT over P. Is it clear? Then Avogadro constant is also a constant, and all these RT and P are constants. Therefore, we can say that V equals to RT over Na times P into capital N, that is numbers of molecules. All right. Then we can say at constant temperature and pressure, we can say volume is proportional to the numbers of molecules. Volume is proportional to the numbers of molecules. So that is the Avogadro. That's how we derive the Avogadro constant. Avogadro. Is it clear? Then for two instances, where V1 N1 and V2 N2, we can say that V1 over N1 equals V2 over N. Now we can rearrange this one. V1 over V2 equals N1 over N2. You can either use this one or this one. For those equations, we can use that. That means volume is directly proportional to the numbers of gas molecules present, because numbers of gas molecules is proportional to numbers of gas moles. Is it clear? So that is called the Avogadro rule. So you can start writing from this point and you can ask the question. Right, have you reached cooking now? Not yet. So then let's move on to the next law. Actually, it's not a law. Now we are going to determine the molar volume of a gas. Molar volume, as it is given by the name, we are going to determine the volume of 1 mole of a gas. For any particular gas, at a given temperature and pressure conditions, the molar volume is a constant. For example, at 0 degrees Celsius and 1 atm pressure, the molar volume of a gas is 22.410, sorry, 414 cubic decimeters per mole. That means at 0 degrees Celsius and 1 atm pressure, 1 mole of a gas occupies 22.4 cubic decimeters of volume. Is it clear? Right. So you can write down the sixth one, molar volume. Right. You can note down since the volume of a gas I forgot to say here this one molar volume is symbolized by Vm. Vm is the molar volume. You can say since the volume of a gas is directly proportional to the numbers of moles, we can write it as Vm equals V over N. Vm equals V over N. Then you can say since temperature and pressure is the same, since temperature and pressure is the same, 1 mole of any gas occupies the same volume. Therefore, we can derive the molar volume like this. We can apply radial gas equation P equals nRT. Then we can rearrange. We can subject V over N equals to RT over P. Therefore, the molar volume equals to RT over P. Okay. Like here, so we saw that mole volume equals to RT over P. Okay. So for this temperature and pressure, we can consider two conditions. We can use a standard pressure, that is 1 atm, and there are two temperature conditions, that is 0 degrees Celsius and 25 degrees Celsius. So there are two different values at at those two conditions. Okay. So we can say then note down there are two sets of conditions. There are two sets of conditions applied for the standard value. There are two sets of conditions applied for the standard value. In the first set of conditions, the temperature is taken as 0 degrees Celsius and the standard pressure is taken as 180. We are expecting there are two sets of conditions. There are two sets of conditions. First condition, at 25 degrees Celsius and 180. Okay, standard pressure. So there we can say molar volume. Since it is standard, we use VMT time. Okay. The value is 22.414 cubic decimeters. Okay. That is per 1 mole. Therefore, it is 22.414 cubic decimeters per mole. For the ease of our calculation, we just use as 22.4. So that is that standard pressure and temperature. Okay. We call this standard pressure and temperature. Then the other condition is at the ambient temperature and the standard pressure. Condition 2. At ambient temperature of 25 degrees Celsius. Oh, sorry, I have written it as 25, it's not 25, 0. The first condition, the temperature has to be 0. But it is at 25 degrees Celsius and 1 atm pressure. M equals to 24.790 cubic decimeters per mole. Those are the two values you have to remember. Basically, you write those values. Those values you have to remember. So what we need to know is that at the standard temperature and pressure, the molar volume of any given gas is 22 point. That's the thing that you have to remember.
So any given gas which behaves as an ideal gas.
Yeah, usually we consider these gases behave as ideal gases. Therefore, we need to mention. We don't need to mention that they behave ideally. For them, we can say that means we approximate, we assume the behavior, ideal behavior of the real gases. Okay. Right. So those are the 6 types of laws that we learn under this.
Yes.
Not the gas laws, under the ideal gas equation. Now these are applied under the ideal gas equation. Is it clear? Right. Then there's another theory called Dalton's law of partial pressure. Right. The concept of partial pressure. Usually, we learn the partial pressure under the topic 12 as well, so unit 12 as well, but here we will be just introducing the partial pressure part. All right. Can I write the topic? Dalton's law of partial pressure. Dalton's law of partial pressure. Okay. Before discussing that part, let me know whether you need a break or not. If you need a break, I can give you a quick break, or else we can continue.
This would be same function. That is
Online students, what is your idea? Do you need a break or not? Online people, video.
I think they are always having a mix.
Maybe. What's your idea? No need. Need for no need. Online. Right. What a question. Okay, but if you need, you better tell me. Right. Now we are going to learn the Dalton's law of partial pressure then. It's like this. Now, let's assume we have a room. Inside this room, there are 3 different gases, A, B, and C. Okay. There are 3 different gases, A, B, and C. Here, now since this room is closed, the total pressure inside the room is created by the pressure exerted by these individual gases. Is it clear? Now there are A gas particles. They will, how does the gas exert pressure on a wall? Now that means in this room we are experiencing some sort of pressure. How does that pressure is created? Come on, we learn. The gas molecules, they are in random motion, so they move and hit the wall of the container or the room. So once they hit the wall and bounce back, they will exert a pressure on the wall. Okay, that means these gas molecules, they move randomly, and then due to the random motion, they will exert a pressure. Now see, if now since it has A gas, that means there are so many K gas molecules inside the vessel. So they will move randomly and hit the wall of the container and exert the pressure. Okay, the pressure exerted by A is called the partial pressure of A. Pressure given by A, that is PA, we call it partial pressure of A. Okay, we call it partial pressure. Why is it partial pressure? Because that PA is only the part of the total pressure inside this system. Okay, so PA is the pressure exerted by only A gas molecules. Then similarly, there's B, they will exert TB, that is the partial pressure of B. Partial pressure. Then C are there, that is PC, that is the partial pressure of C. Is it the partial pressure of A, partial pressure of B, and partial pressure of C? Got it? Now, those are the three pressures that will be exerted by these A, B, and C gas molecules on the walls of the container. So the total pressure inside the system will be the sum of these three. Is it clear? So therefore, you can say the total pressure. That is CA plus CB plus CC. So this is called the Dalton's law of partial pressure. Dalton said that the total pressure inside the vessel is equal to the sum of the partial pressures of the constituent gases. Is it clear? So that is the Dalton's law of partial pressure. Did you write the topic? Right. Then you can note down. The total pressure exerted by the total pressure exerted by the mixture of non-reactive gases the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressures of individual gases. Is equal to the sum of the partial pressures of individual gases. This is known as the Dalton's law of partial pressure. Right. Then you can note down, if we consider in a separate point, if we consider a system where gases A, B, and C are present, where the gases A, B, and C are present, they will have the partial pressures of PA, PB, and PC. The total pressure will be given the total pressure will be given by the total pressure will be given by the sum of the partial pressures. By the sum of the partial pressures. Right. So you can copy down this. Okay, finish. Right. Then let's consider gas mixture of A and B. Now we are going to define this one. Right. In a new point you can write down. Let's consider a gas mixture let's consider a gas mixture of capital A and capital B. A and B. So let's see how to apply the ideal gas equation for this. You can say by applying ideal gas equation, this is for the gas mixture of A and B. Can apply ideal gas equation. PV equals nRT. We can apply the gas equation. Then for A, pressure will be PA and the volume will be V. Numbers of moles will be Na into RT. That is for the gas A. Then from there we can subtract Na, that is PA V over RT. Let's take this as the first equation. Okay. Then similarly for B, we can apply ideal gas equation. For the gas B, EP times V equals NV times R. Then NV equals PV times V over RT, that is the second equation. Now we know that the total gas moles that is NP equals Na plus NB, because A and B are the constituent gases. So the total number of gas moles will be equals to numbers of moles of A plus numbers of moles of B. Is it clear? Okay. So then we can replace these values with our known values. So from this one we can apply the total numbers of moles. That is total pressure into volume divided by R. So NT equals to the total pressure into volume divided by RT. Pressure of A into volume divided by RT plus pressure of P into volume divided by RT. Alright. Then P over RT is a constant. So we can say that the total pressure equals PA plus P. Okay. So that is how we derive the ideal gas equation. Is it clear? Did you understand the ideal gas equation or property? Right. So then you can copy this down. Right, finish. Okay. So that is the Dalton's law of partial pressure. Right now we can express this Dalton's law of partial pressure in the form of mole fractions as well. Now here we have expressed in the terms of pressures. So we can express in the terms of mole fractions as well. So in a separate point you can write down the partial pressures can be expressed in terms of mole fractions. Partial pressure can be expressed in terms of mole fractions. Okay, so let's see how to express in the terms of mole fractions. So we express it like this. Now let's assume the gas mixture. Now for that we can apply P equals NR. Let's assume there are two gases A and B. Right. So we can find out the partial pressures PA and PB in terms of the numbers of moles, temperature, and the volume. Right. So applying ideal gas equation, we can say PB equals NRT. Then for a mixture of A and B, we can apply PB equals NRT. So we can say that PA equals NA times RT over B. That means we can subject pressure over here, P equals NRT over B. Similarly, we can give PB equals NB times RT over B. Okay. So according to the Dalton's law of partial pressure, according to Dalton's law of partial pressure, we can say that the total pressure equals PA plus PB. PA plus PB. So we can rearrange. We can replace PA with this one. NA times RT over B plus PB equals NB times RT over B. Is it clear? Right. So RT over B is a common term. So we can take it out. So therefore, PB equals Na plus Nb times Rp over. Is it clear? So that's how we subject this one. Then this is for the total pressure. Then the partial pressure of A is there, partial pressure of B is there. Okay. Now we can get the ratios between them. Let's say this is 1, this is 2, and this is 3. We can divide 1 by. So that is PA over PT equals NA times RT over V divided by NA plus NB times RT over V. Then RT over V is a constant, we can cancel them off. So PA over PT equals NA divided by what is NA plus NB? The total numbers of moles, because in this system we have A and B. Then we can rearrange this one. PA equals. Now usually we call NA over NB as X. And give it NA divided by NA plus NB into P total. Now this is called XA, is the mole fraction of A, that is NA divided by the total numbers of moles. Mole fraction of, that is XA equals to NA divided by the total numbers of moles. So therefore, we can say that PA equals XA times total pressure. So this is how we express the partial pressure in terms of mole fraction. Okay. Similarly for XB, we can express PB equals XB times total pressure. Now there XB equals B equals NB divided by NA plus NB. So likewise, we can express the partial pressures in terms of the mole fractions in this manner. Is it clear? Right. So you can copy it out. Finished. Anjali, are you finished? Shall we continue? Online people, I think you have finished copying down. So then let's continue with the question. You can note down the question. Right. So let's move on to the question. You can note down the question. The partial pressures of hydrogen and helium in a gas mixture are. Partial pressure of H2 and helium in a gas mixture are. One into 10 to the power 5 pascals and 4 into 10 to the power 5 pascals respectively. One into 10 to the power 5 pascals and 4 into 10 to the power 5 pascals respectively. The volume of the gas mixture is 1.5 cubic decimeters. Volume of the gas mixture is 1.5 cubic decimeters. The volume was changed to 6 cubic decimeters. While volume was changed to 6 cubic decimeters, while keeping the temperature the constant. So we are keeping the temperature at a constant value. Assume that hydrogen does not react with helium, and both gases behave ideally. Assume that hydrogen does not react with helium. Both gases behave ideally. And calculate Number one, partial pressure of advent in the new volume. Second one, partial pressure of helium in the new volume. Third one, initial pressure of the gas mixture. Fourth one, final pressure of the gas mixture. So these are the things that you need to calculate. Okay. So shall we make them one by one? Do the first one and second one, calculate partial pressures.
It's
Then you get one by one. Partial pressure.
okay.
Five.
Go out and stay here, TV use.
Sorry.
Shall I go out and stay here, TV use?
That's okay.
Next week, I will go to class.
Sorry. Okay. Do you need a gas mountain for that? Okay, so we define the first one. Partial pressure of hydrogen in the new volume. Right. We need to find out partial pressure of hydrogen in the new volume. Now the partial pressures of hydrogen and helium in gas mixture are 1 into 10 to the power 5 pascals and 4 into 10 to the power 5 pascals. This is hydrogen and helium. Those are the initial values. That is in the volume of 1.5 cubic deciliters. Volume is there. Then in the second case, the volume was changed to 6 while keeping the temperature a constant. Now see, the temperature is a constant. So at constant temperature, the relationship between pressure and volume is the Boyle law. Right. So for the first one, we can apply the Boyle law. For the first one, we can say applying Boyle law. We can say P1 V1 equals P2 V. Right. So the initial pressure of hydrogen is 1 into 10 to the power 5 pascals. And the initial volume was 1.5 cubic deciliters. That means 1.5 into 10 to the power minus 3 cubic meters. Then we need to find out the new pressure, partial pressure of H2. Let's say pH2. And the new volume is 6 cubic deciliters. That means 6 into 10 to the power minus 3 cubic meters. Then we can find the pH2. That is 2.5 into 10 to the power 4. Ten to the power minus 3 gets cancelled off. 1.5 and 6, 4. We have divided this by 4. 10 divided by 4 is 2.5, that is 10 to the power. So that's it. Then for the second one also, partial pressure of helium in the volume. Again, we can apply the Boyle law like that. And we can find the value. By applying Boyle law. That is P1 equals V2 V2. 4 into 10 to the power 5 pascals is the pressure. And the initial volume was 1.5 cubic deciliters. That is 1.5 into 10 to the power minus 3 cubic meters. New pressure, that is P helium. And the new volume is 6. Then we can find out the partial pressure of helium. That is 1 into 10 to the power 5. Okay. The third one, initial pressure of the gas mixture. What is the initial pressure of the gas mixture? That is, initially we have hydrogen and helium in these two pressures. So we have to add those two together. Okay, 1 into 10 to the power 5 pascals plus 4 into 10 to the power 5 pascals. Answer will be 5 into 10 to the power 5 pascals. Then the fourth one we need to find out the final pressure. That is hydrogen is 2.5 into 10 power 4. And helium is 1 into 10 power 5. Answer will be 1.25 into 10 to the power 5. Total final pressure will be like this. Is it clear? What's the going to do that? A mixture contains iron oxide, Fe2O4. When a sample of 5.52 of this mixture is dissolved in dilute sulfuric acid, 20 cubic centimeter of 0.1 in potassium permanganate is required to complete reaction. Now we have Fe2 plus and Fe3 plus in these two. And Fe2 plus is the one which can undergo further oxidation. Fe3 plus it cannot undergo further oxidation. So once we add potassium permanganate is an oxidizing agent. So it will react only with this fraction. It does not react with Fe3 because it is in the Fe plus 3 oxidations. So if we can find out the numbers of moles of potassium permanganate added, then we can write the balanced equation between Fe2 plus and permanganate. And we can find out the numbers of these. How many people will discuss this? Yeah. Right now, is it clear? So that is how we apply the partial. Then the next thing that we need to discuss is the molecular kinetic theory of gases. Time is not enough for starting the theory part today. So therefore, let's see another question regarding these gas equations that we have learned. Now, in this unit, in this gas laws unit, there are two main equations. One is the ideal gas equation. Other one is the equation of the molecular kinetic theory. Okay. Ideal gas equation we know that is PV equals nRT. And the molecular kinetic theory, the equation is PV equals 1/3 mNc square rho. So those are the two main equations that we have learned in this video. Right. Now we have learned all the theories related to the ideal gas equation, that is PV equals nRT. PV equals nRT. Then we have to discuss the other equation, the equation of molecular kinetic theory. So then that will be the end of this unit. So we can discuss the theory part next week. So let's see another question up to from this. I'll give you a question. Right, so this is the question. Now you are given a system of two bulbs. Right, now you write the question. First of all, we need this. So we have a system, two bulb system like this. So in the first bulb, okay, let's name these two bulbs as A and B. A and B. So A has heat and B has neat. Two gases are present. So the volumes will be, this one is 5 cubic meters volume. This is 2 cubic meters. 5 and then the pressures inside them are 1 into 10 to the power 5 and 5 into 10 to the power 5. The pressure inside this one is 1 into 10 to the power 5 pascals. Pressure inside this one is 5 into 10 to the power 5 pascals. Okay, then the temperatures in these two bulbs are 300 Kelvin. Both are at 300 Kelvin. So that is the initial system. Okay. You can note down. Two gases, helium and neon. Two gases, helium and neon, which behave ideally, are placed in a system as follows. Are placed in a system as follows. Peppers. All right. Then we can say, assuming the ideal behavior, of helium and neon, answer the following questions. Answer the following questions. You can say, first one, calculate the partial pressure of neon. Calculate the partial pressure of neon inside the vessel B. Calculate the partial pressure of neon inside the vessel B. Once the tap is opened and the system is heated to 500 Kelvin. Once the tap is opened and the system is heated to 500 Kelvin. Let be second question. Calculate the partial pressure of helium. Calculate the partial pressure of helium inside the vessel B. Inside the vessel B. At the temperature of 500 Kelvin. At a temperature of 500 Kelvin. After opening the tap. After opening the tap. Then the next question. Third one. Right. Calculate the total pressure in the system. With the total pressure in the system. Then the fourth one. Calculate the ratio of partial pressure is to total pressure. Calculate the ratio of partial pressure is to total pressure of helium in the gas mix. Of helium in the gas mix. Alright, so those are the four questions. You can answer them now. If you find the answer for the first one. Yeah, that's it. Sorry, 8.3. Ah, 8.3 and 10 to the 5. Right. Online students, did you find the answer for the first one?
No.
No? Come on. Now see, initially we had this one. No, so let's see the answer. So you have find out the partial pressure of neon inside the vessel B under new conditions. So the new conditions are we are removing this tap, that is we open the tap and this is heated up to 500. Now none of the gas molecules have been inserted or taken out of the system. So the numbers of gas molecules is the same. And the volume is also the same because there's no any volume change. Come on, there's a volume change. Initially, neon was in this 2 cubic meter volume. Now, once we open the tap, what will happen? It will disperse throughout this whole volume, that is 7. So, there's a volume change. So, volume is not constant. And temperature is also not constant. Temperature has also been increased. Then the pressure too will be increased. So, what is the law that we can apply for this one? Yeah, combined gas. Then for the first one, we can apply the combined gas law. You can say applying the combined gas law. We can say P1 V1 over T1 equals P2 V2 over P2. So initial pressure, that is 5 into 10 to the power 5 pascals. Initial volume was 2 cubic meters. Initial temperature was 300 Kelvin. New pressure is the thing that we need to find out. Let's say it is pressure of neon. New volume is 5 plus 2, 7. New temperature is 500 Kelvin. Now we need to simplify this one and find the partial pressure of neon. Okay, what is it? Fifty divided by 21. Answer will be 2.38. 2.38 into 10 to the power 5. 2.38 into 10 to the power 5. So this is approximately, we can take it as 2.4 into 10 to the power 5. So that is the partial pressure of neon inside the vessel. Then the second one is calculate the partial pressure of helium inside the vessel. Right. So whether it is inside B or A, it's always the same pressure. No? Because now this, once we open the tap, this whole system has become one system. Second one, we can again apply the combined gas law. That is P1 V1 over P is P1 equals P2 V2 over P2. Initial pressure of helium, it is 1 into 10 to the power 5. When the volume is 5, temperature is 300. New pressure is the thing that we need to find out. Pressure helium into new volume is 7. New temperature is 500. Then we need to find out the pressure of helium. That is 1.2. 1.2 into 10 to the power 5 Pascals. Okay. Then we need to find out the total pressure inside the system. So total pressure equals partial pressure of helium and partial pressure of neon. What is this law? Dalton's law of partial pressure. So we have to write applying Dalton's law of partial pressure. That is the assumption you have to take. Applying Dalton's law of partial pressure. So total pressure equals to 1.2 into 10 to the power 5 Pascals plus 2.4 into 10 to the power 5 Pascals. Altogether 3.6 into 10 to the power 5 Pascals. Okay. Then we calculate the ratio of partial pressure of helium to total pressure. So partial pressure of helium, it is 1.2. Into 10 to the power 5 is to 3.6 into 10 to the power 5. So answer will be 1:2. That is the ratio. That's a quick. So that's how we find these values. Okay. So that is the end of the first part of this lesson. Then, as I have promised you, next week we will be discussing the molecular kinetic theory of gases and okay. Then that will be the end of this unit. So within another couple of weeks, we can start the next unit, that is enthalpy, energetics. Why are you smiling?
No, do we have to draw those diagrams?
Enthalpy. There are things that we have to draw the thermochemical cycles, enthalpy level diagrams, and Born-Haber cycles. And also we have to learn about 14 types of enthalpy changes. It's a somewhat lengthy lesson, but easy. I think according to my experience now, in this year I'm going to celebrate the 10th year of my teaching, right? So then that is next year, is 2024. In 2025 will be the 10th year that I'm teaching chemistry. So according to my experience, energetics is the lesson that the students find most easy of these chemistry lessons. So it's very easy. These are also easy, but energetics is the one that every student can do. Each and every student try it. All right. Okay. So then from this point, I will be ending the class for today. And let's meet on tomorrow for the paper class at 3 o'clock. Huh? Right. Because the other people, they requested to start at 3 o'clock. That's why. Okay, so let's do the paper class from 3 to 6. All right. Okay, then that's all. Have a nice day.